in terms of sizing. Generally speaking, there are four main topologies in order to realize a DVR. They mostly vary in terms of energy provider unit of the DVR. For this project, a DVR with a supercapacitor as a storage media has been developed and analyzed in MATLAB. There are three main strategies in order to control a DVR, including voltage quality optimized control, which compensates the voltage dip to the same exact value of the dip of the voltage, both in terms of magnitude and phase angle. Voltage amplitude optimized control, which minimizes the amplitude of the injected voltage, and energy optimized control, which minimizes the energy consumption of the DVR during voltage dip. You can see these three strategies in the phasor representation for a resistive load. Installing a DVR would solve the problem of voltage dip as a result of faults in other parts of the network. But faults do occur on the distribution feeder downstream the DVR. As a result of this fault, a large current will pass through the DVR, which can easily damage it, especially the power electronic switches. Also, the subsequent voltage dip is damaging for the parallel loads. Relying only on the upstream circuit breaker to break the short circuit current may take some cycles to achieve. Let's consider a specified low voltage distribution network with the parameters depicted in the picture. In order to provide appropriate protection coordination for this network, a complete fault analysis is supposed to be done. In the picture, you can see the simulation results in MATLAB environment for high index of fault current and low index of fault current. High index term implies fault occurs at the M-bus at the moment, which results in the highest possible DC current component, and low index term implies fault occurs at the load bus at the moment, which results in zero DC component. In order to protect this network, a low voltage circuit breaker with this characteristic here is installed in front of the M-bus. The instantaneous tripping is set on 10 times the rated current due to network requirement, because this network is supposed to be robust enough against the inrush current of big motors. Now, DVR is inserted to the same network. An often used option for a DVR during downstream fault is protecting it by enabling a bypass circuit. It's a trivial conclusion that bypass circuit would only protect the DVR and allow a large fault current to flow in the feeder, which results in considerable voltage drop at the upstream buses. You see the high index of fault current, which is as high as 45 per unit, and also the bus voltage upstream the DVR. The very short value is due to voltage drop across the static switch of bypass. The more promising approach is to integrating a fault current limiting function into the DVR. For this purpose, there are two main strategies, including passive strategy and active strategy. Passive strategy implies inserting passive elements into the faulted feeder in order to limit the short circuit current in such a way that avoid interfering with upstream circuit breaker. Active strategy implies controlling the DVR in such a way that it can inject a suitable voltage to limit the short circuit current to 1 per unit. So, for this strategy is required to implement a communication channel between the DVR and upstream circuit breaker. The first passive strategy that has been analyzed in this project is based on employing the short circuit impedance of the injection transformer. As you see, there is a bypass, there is a static switch at the secondary side of the injection transformer. As soon as fault is detected, the control system turns off the converter and fires the static switch. You can see the simulation results for this strategy in the figures for high index and low index. The problem of this strategy is that for high index of fault current, the imposed fault current limiting is not sufficiently effective and voltage of the M-bus drops below 50%. The second passive strategy is based on employing the reactance of the filter. As you see, the static switch is moved in front of the converter. As soon as fault is detected, the static switch is turned on. The problems of this strategy are the very strong current limiting imposed on the short circuit current, which causes interfering with upstream circuit breaker, and the second problem is a high value of ratio X over R in the faulted feeder, which results in a slow decaying DC current component that puts stress on the upstream circuit breaker because of increasing the parameter of lead-through energy. The third passive strategy is based on merging the fault current limiting function with the bypass strategy. For this purpose, an additional inductance is inserted into the protection scenario in series connection with the static switch number 1. As soon as fault is detected, the static switch number 1 is turned on in order to limit the short circuit current. But the control system continuously measures the line current. If the line current becomes lower than 10 times rated current, then the static switch number 2 is turned on in order to let the current increases to be detected by upstream circuit breaker. You see the simulation results for high index and low index. As you see in the high index, effectively the short circuit current is limited and the bus voltage is restored to more than 65%. Also, it's possible to increase the level of fault current limiting from 2 levels to 3 levels by introducing the static switch number 3, which is still under investigation. Active impedance fault current limiting mode. Let's consider the normal operation condition for the same previous network. In order to facilitate the discussion, the feeder is assumed lossless and the short circuit impedance of the injection transformer is neglected. Then a fault occurs downstream the DVR at the location of F, which is a random location downstream the DVR. You can see the phasor representation of voltages and current in the picture.